Hello everyone, I am Dr. P.S. Patil. Welcome you all to my YouTube channel. In this video, we'll be discussing about image enhancement methods in spatial domain. So first of all, we'll understand what is this image enhancement process, and then we'll discuss about different enhancement schemes or methods that are classified as spatial domain enhancement method, frequency domain enhancement method. Then they are broadly classified as point operations for enhancement, neighborhood operations for enhancement, and there are some histogram methods that are also used for image enhancement. So first of all, we'll understand what is spatial domain enhancement and what is frequency domain enhancement. So spatial domain is where we are directly working with the pixel values in the image plane, whereas frequency domain is where we are transforming image under consideration into frequency domain by Fourier transformation, and we are working on spectral components of an image. So this is indirect method of image enhancement where we are manipulating the spectral components of the image, and after this manipulation we can come back to the spatial domain by inverse Fourier transformation. So sometimes in the spatial domain there is a certain information regarding the spectral contents or frequency components of the image hidden in the spatial domain. So you cannot see the spectral components or frequency components in an image when you work in the spatial domain. So when you take your image into the frequency domain, you can see that hidden information about the spectral content, and accordingly you can decide upon which kind of transformation will be suitable for the given image, so that it will be more suitable for our application. So frequency domain transformation is indirect method of transformation where we are working on spectral components of the image. We are manipulating the spectral components, and then that modified image in the frequency domain we are taking back into the spatial domain by inverse Fourier transformation. Whereas spatial domain, as I told you, is where we are working directly with the pixel values of an image. We are manipulating the pixel values of the image, and that is how we are trying to enhance the image. We are trying to make it more suitable for our application. Now, what is point operation and neighborhood operation? In point operation, we are manipulating the candidate pixel alone without considering its neighbors. So the transformation acts on a single pixel at a time, and this we are repeating for all the pixels in the given image, and that is how we are trying to enhance the given image. We are trying to make it more suitable for our application. Whereas unlike to the point operation, in neighborhood operation, it is not only the candidate pixel, we are also considering neighborhoods of the candidate pixel in the operation of enhancement, and therefore it is called as neighborhood operation. So neighborhood operation is where we are working on group of pixel to modify one pixel's value called the candidate pixels. So candidate pixels value is not decided based on the present value at the candidate location, but it is decided based on its neighborhoods as well. Then there are some histogram methods also that are used for the enhancement process. So let us first understand what is image enhancement. The image enhancement, as I said, is the process of modifying the image and making it more suitable for specific application. So there are different methods or schemes that are there to do this image enhancement, and they are broadly classified into different types. So as shown here, the image enhancement methods are classified as there are some point operations that are used for image enhancement, such as contrast stretching is there, noise clipping is possible, window slicing is there, and histogram modeling is there. As far as spatial domain methods are considered for image enhancement, they are classified as noise smoothing operation, median filtering operation, then low pass filtering, high pass filtering, band pass filtering, zooming. These are some of the examples of transformations or image enhancement schemes that works in the spatial domain, where we are directly uh, applying our transformation on the pixel values in the spatial domain. In transform domain operation, we are transforming our image into some other domain like frequency domain, or so for that we are using like Fourier transformation or wavelet transformation. So we are taking our image into a transformed domain, and then there we can do the filtering, like linear filtering will be there, root filtering is there, uh, homomorphic filtering is there, and then the another classification of image enhancement method as far as color images is concerned is pseudo coloring. And these are the methods like false coloring and pseudo coloring are the methods used for image enhancement. Now we'll look at spatial domain transformation, which is mathematically defined as g of x comma y equal to capital T of f of x comma y. This is how mathematically we can define spatial domain image transformation method used for image enhancement, where f of xy is input image. So image is a digital representation or numerical representation of visual information. So we are representing image as a two-dimensional matrix, right? And this is mathematically written as f of x comma y, where x and y are spatial coordinates, and function f returns what? The intensity value of the image at location x comma y. So f of x comma y is a two-dimensional array or matrix that represents image for all the values of x comma y, whereas g of x comma y is another two-dimensional vector we are using or matrix to represent the output image. So this modified image g of x comma y is result of what? The application of the transformation on image under consideration for image enhancement, defined as f of x comma y. So t is an operator, or this is the transformation operation that applies on f, right, where f is the original image and g is modified image. So in this transformation, as far as spatial domain transformation is concerned, to modify the pixel value at location x comma y, we are considering not only the original pixel at location x comma y, but also its neighborhoods, right? uh, the 8 neighborhoods normally we are considering of the candidate pixel at location x comma y. So the horizontal neighbors, vertical neighbors, and diagonal neighbors, they are also considered in the spatial domain neighborhood transformation to decide the new value of the pixel at location x comma y. Now this spatial domain enhancement methods, as we know now, is the technique performed in the image plane itself. It is the technique where the transformation applies directly on the pixel values. It is the technique where we are modifying the pixel values directly, right? So this is called as spatial domain transformation, and in this process we are modifying the pixels directly by considering the transformations of the type point operation and spatial operations. Now we understood what is point operation and spatial operation. So in point operation, transformation applies on the candidate pixel alone, right? So whatever is the transformation operation, transformation function, that operator we are applying on the candidate pixel alone, right? And that results into new value of the candidate pixel. Whereas in neighborhood operation, neighborhood spatial operation, it is not only the candidate pixel, we are considering some neighbors. It may be 4 neighbors or 8 neighbors or it may be 16 neighbors we are considering of the candidate pixel. So to decide the new value of at location x comma y, right, we are considering the present value at location x comma y as well as uh, some neighborhood pixels of x comma y in spatial domain. Uh, neighborhood operation. So frequency domain enhancement methods is where we are taking our original image into the frequency domain, and we are working with what transformed coefficients. So transformed coefficients or spectral coefficients in the frequency domain, they are manipulated, and then that modified image we can take back into the original spatial domain by reverse transformation using if I'm taking image into the frequency domain by FFT, by inverse FFT we can take that the modified image back into spatial domain. Now this is the first point transformation method, contrast stretching. So the idea behind contrast stretching is to increase the dynamic range of gray levels in the given image. So the basic principle is to make the brighter portion of the given image more brighter and darker portion of the given image more darker, so that the dynamic range of gray values will be wide enough, right? So this is the transformation you can see. U is the pixel value in the original image, where V is the new pixel value, modified pixel value, and you can see the curve that is used for the contrast stretching transformation. So there are some levels you can see on the horizontal axis and on the vertical axis. So mathematically it is modeled as contrast stretching. uh, the new value v, small v of pixel uh, is equal to alpha into u, where alpha is this angle, and this transformation works for value of u between 0 to a. So for value of u between 0 to u a, it is defined with this line, and it is mathematically defined as v is equal to alpha into u. V is equal to alpha into u. Whereas for a value of u between a to b, it is this curve that is used for the transformation, with beta is this angle, and the modified value of v mathematically can be written as beta times u minus a plus va. So this curve starts from va, and therefore this plus va is there. So this curve starts from va, and you can define this mathematically as beta times u minus a plus va, where u, as I said, is original pixel value, a is this, right, and v is modified pixel value. Next, between for value of u between b up to the last pixel value l, so value of u between b to l, it is this curve used for the transformation, and it is mathematically defined as v is equal to gamma times uh, u minus b plus vb. So it is starting from b, right? So this, therefore the vb is there, whatever gray level in the original image is there, right? uh, it starts from vb. So vb plus gamma times u minus b. This is the transformation for value of u between b and l. So this is contrast stretching. The basic principle is to make the darker portion more dark and brighter portion more bright. So contrast stretching is the transformation where we are increasing the dynamic range of gray values in the given image, and it is by uh, making the darker portion more dark and brighter portion more bright, we can enhance this dynamic range, or we can enhance the contrast of an given image. So contrast is what? Contrast is the difference between black and white pixel, difference between the total dynamic range of gray values, intensity levels. So if that is wider image, it is called as better contrast image. So if the given image is poor contrast image, then its contrast enhancement is possible, and thereby we can enhance the given image by using this contrast stretching transformation, which is mathematically defined like this, and the transformation curve you can see like this. So if you do the extreme contrast stretching, the another result you will get, and the result is black and white image or binary image. So thresholding is the transformation. It is a type of image enhancement transformation that results into black and white image or binary image. So it is what it is called as extreme contrast staging. So as seen in the transformation curve, you can see U on the horizontal axis is the original intensity levels, V is modified pixel values. So modified pixel values are 0 and L. L is the maximum gray level in the given image. So there are only two values in the modified image, you can see 0 and L, and therefore the resultant image after application of this transformation is binary image. Binary stands for two level image. So two possible values of gray are what? 0. 0 represents black pixel, and L is the highest pixel value. For example, if it is 8-bit image, L is 255. So 0 and 255, these are the two values in the resultant image you can see after application of this thresholding transformation on the given image. So this thresholding is nothing but extreme contrast stretching, and it results into two level image, also called as binary image or black and white image. So all the pixels will take only two values, either 0 or 255. So this is what is the result of this transformation called as thresholding transformation. The another widely used transformation is digital negative transformation. The transformation curve you can see here with respect to R. R is the pixel value, so, and S original pixel value, and S is modified pixel value. So this transformation mathematically can be defined as S is equal to transformation on R, and it is given as L minus R minus 1. So the realization of this equation is this line on the transformation curve. So this transformation, if you apply on the given image, for example, if R is equal to 0, you can put it here, R equal to 0. Right? Then what is the result is S is equal to L minus 1. For example, for 8-bit image, L is equal to 2 raised to 8 minus 1, 2 raised to 8. So 2 raised to 8 is 256, minus 1 is 255. So in the original image, if the pixel value is 0, that is transformed as 255. If in the original image the pixel value is L minus 1, that is 255, it is transformed as 0. And the same is true. This transformation you can apply for all the values of the possible values of the pixel, and this the realization of this equation is this line. This line is called as digital negative